in a previous video, I sort of said I would do this, so now I'm going to do this. And that's going to show you how to build these visual models of a pendulum in Python. And I use this in my my video about how to calculate all the different ways to calculate the motion of a pendulum. And so really I'm going to use, a lot of them do the same thing. So I'm going to use this first idea, creating a differential equation with Newton's second law, and then we're going to model that. And then I'm going to come back and do the second way, because those do display a slightly different amount. Okay, so here's your basic pendulum. Has some mass hanging by a string supported up there. It's at some angle theta. And so, you know, this is really tough because there's a tension pulling this way that we can't really calculate. So what we do instead is to say, okay, let's call this the S direction. And so the mass can only move along that direction. And if I do that, I can say F net in the S direction is m times AS, the acceleration in the x direction. That's Newton's second law. It still works if that's my dimensional way. Okay, let me go ahead and write this as ms double dot. So s double dot is just going to be the second derivative m, the second derivative of s with respect to t. Okay, and the double dot is just a notation that looks cool we like to use. It's actually shorter too. Okay, so if I look right here, then if s is that way, then the force is going to be negative mg times this component right here, which is the opposite side. So this is going to be negative mg sine theta, and that's just going to be ms double dot. So then I have two variables here. My angle theta is changing, and my acceleration is in the variable s and s double dot. And I want to get that all in the same thing. So if this is down here and it moves a little bit, I can say s equals r theta, right? Because if I move it some small amount, theta, it's going to move in the arc length s. That's the arc length. And then I can take the derivative, s dot is going to be r theta dot. R doesn't change. And then s double dot is r theta double dot. Okay, so now over here, this becomes negative mg sine theta equals mr theta double dot. And that's what I want. Right off the bat, you see the mass cancels. If I solve this for theta dot, theta double dot, I get negative g over r sine theta. And that's the answer. Okay, that's my differential equation for the motion of a pendulum. If you assume theta is small, you can replace sine theta with theta, which we'll do later. But right now we want to solve this differential equation. So how do you do this? One way is with a numerical calculation. Okay, so here's my equation. Theta double dot negative g over r. I'm calling it r because I was going to use angular momentum. You could call it L. You could call it whatever you want. Sine theta. Okay, so now imagine that I break this into small time intervals of delta t is 0.01 seconds. I just picked that value. Then I can write theta double dot, the second derivative of theta, like this. I can actually say theta double dot is delta theta dot delta t. So it's the rate of change of theta dot, which is the angular velocity. And if I consider at the beginning of the time interval, I'll draw a little picture right here. So here's theta, and it's moving, let's say, that way. So it's theta 1 dot, and then a little bit later after delta t, it's right there, theta 2 dot. Then I can say this is theta 2 dot minus theta 1 dot over delta t. And this assumes that theta double dot's constant, which it's not, but it kind of is, right? So if we have a small time interval, we can assume theta double dot's constant. I know you're thinking, hey, this is bogus. It's bogus. You can't do that. Well, I can, and you can't stop me, okay? But you know, in the end, if I make these assumptions and I get good answers, then it's fine. It's kind of like the Kobayashi-Maru problem of Star Trek, right? If I win the game, then it doesn't really matter that I cheated. I am cheating. If I multiply both sides by delta t and add theta 1, I get theta 2 dot equals theta 1 dot plus theta double dot delta t. And remember, I can calculate theta double dot, so I can use this to find theta 2 dot at the end of the time interval. That's important. Okay, so now I need to do the same thing with theta dot and theta. So I can say theta dot is delta theta delta t. So it's going to be theta 2 minus theta 1 over delta t. Again, now I'm assuming that theta dot's constant, which I just changed theta dot. And you're thinking, what? Can't do that. Can, will, am gonna. Okay, so let's just solve this for theta 2. I'm going to say theta 2 equals theta 1 plus theta 2 dot delta t. And I know I didn't have a 2 right there. But since I just updated theta, I'm going to use the theta 2 theta dot. I'm going to use theta dot that I just calculated. T2 equals T1 plus delta t. Update time. And then just go back up and do it all again. Okay, so this is the Euler method of a numerical calculation. Now, important to note, it does depend on delta t. It does depend on the order too. It turns out you can try that if you want. But it also, I need to know theta 1 dot theta 1. I don't know, I'm picking something, 20 degrees. I need to know the initial angular velocity, and I need to know the initial angle, right? Once I do that, I can calculate theta dot, double dot, depends on the angle. But then in order to update theta dot, I need to know the original theta dot. So I need to have a starting value for the velocity and the position. But after that, I can do it. So let's go ahead and jump over to Python. We're going to build an actual model, a visual model. It's going to be awesome. You're going to love it. I'm going to have fun. We're all going to have fun. We do need numerical values. I do need the values of theta. I need the value of g. I need the value of r. So let's just make a meter-long pendulum just because I think that's easy. Okay, I'm jumping over here to Python. Hello, here we are. I'm using GlowScript. This is WebVPython in Trinket. It's in Trinket, but it's still WebVPython. You can do this on WebVPython, and it works just fine. So I'm going to do everything from scratch right here. Let's start off with our constants. So I'm going to say g equals 9.8. Now notice in this case, I am saying g is the constant, right? I'm not using g as a vector because I've already kind of scalarized it in my differential equation. So I could do the magnitude of it, but let's just call it g. R equals 1. That's my length of the pendulum. It's kind of long, but there's something good about that. Theta equals, I need to have some starting angle. Let's say let's do 15 degrees. And Python, this one likes radians better. There's a way to do it in degrees, but I'm just going to convert this to radians right here. So times 2 times pi divided by 180. If you're coming from numpy, whatever you want to call it, WebVPython has a lot of that stuff built in, so you don't have to import a module for that. So you can just use pi. And then I need the initial angular velocity. I'm going to call this theta dot equals 0. So I'm going to start it from 0 radians per second. I need my time, t equals 0, dt equals 0.01. Okay, so now I need to make my physical objects. So I'm going to make this as a top pivot point and then a mass down below. And then I'm going to have a string connecting them. So let's call this top is a sphere, position equals vector 0. I'm going to shift it up a little bit. I don't want to have it right at the origin. I'm going to have this as r over 2, 0, comma. And I got rid of my thing right there. And then I'm going to say the radius is going to be equal to r over 20. I'm going to not give it any other properties, so it'll be a gray sphere right there. Let's go ahead and run that. I can show you what it looks like. So this is the power of WebVPython, is that we can make these three-dimensional objects very easily. Sphere is a built-in three-dimensional object, and there it is right there. And I'm rotating around this 3D space. So I mean, it's kind of weird, but I want to make it a little bit smaller. Let's say 30. Okay, now I'm going to make my mass. Let's just call it a ball, sphere. where is it going to be? So if I should have drawn this picture, but if I have some angle theta and I have the length r, this vector from the top to that other location is gonna, I need to say negative r cosine theta, that's in the y direction, positive r sine theta in the x direction. So I'm going to say the position is equal to top.pos, because I want to attach it to there, plus r times vector sine theta, negative cosine theta. So this is the y direction, this is the x direction, this is the z direction. Cosine theta, 0. The radius, I'm going to say radius is equal to r divided by 15. That might be too big, I don't know. And let's give it a color of yellow. Color dot yellow. And let's say make trail equals true. That's going to, when it moves, it'll leave a trail behind. Okay, so let's run that. Okay, so there's my top point, there's my mass down there, and that angle should be 15 degrees. Okay, now I need to create a string to connect the top to the bottom. There's more than one to do this. I like to use the cylinder object. So let's say string equals cylinder. And you can find a list of all the objects on webvpython.org. They have a cylinder, spheres, boxes, helixes, stuff like that. So a cylinder has two important properties. One is the position. And that's the location of one, this is a cylinder, one end of the cylinder. The other is a vector from that location to the other end. Okay, so I need to give a position and a vector, which we call the axis. And then I also need to say the radius. So let's say its position is going to be top.pos, right? It's going to start up here at that location. And then its axis is going to be equal to from the top to the ball. So I can just say ball.pos minus top.pos. I could do that same vector, but I don't need to do that. And then I need to give it a radius, let's say r divided by 45. And then that's it. I'll leave it as gray, white, or whatever color that is. That's a little thick. Okay, let's do 65. It's got to look good, right? It's not just good to calculate good. Well, it's got to look good, and I think that looks pretty good. Let's make it a little bit thinner, 85. I like to do it in terms of r because then I know my dimensions. Okay, I'm pretty happy. Okay, so now I have that. What I need to do is to calculate the new value of theta and move everything, and that's what I'm going to do now. So I have my t, I have my dt. Let's make a loop. While t is less than, I want it to run for 3 seconds. Now, this is an important line right here, rate 100. Since rate 100 tells Python, don't do more than 100 of these loops every second. And since I have a dt of 0.01, this would make it run in real time. You can change this. I can make it run fast, or I can make it run slow by changing the rate value or the dt, right? Okay. So now the first thing I want to do is to calculate theta double dot. So I haven't declared that variable, and that's fine. I don't need it until now. So I'm going to say theta d dot. That's for my double dot. It looks a little weird, but that's just something that I like. Now it's going to be equal. I'm just using my equation for my differential equation. Negative g times sine of theta divided by r. Divided by r. That's theta double dot. Now I have theta double dot. I can use that to update theta dot. So theta dot equals theta dot plus theta double dot times dt. And so you'll notice here that this is a Python thing. It's in computer science too. In that I don't have to do indices, right? What I'm doing is I'm taking the value of the current value of theta dot, which starts off at 0. I'm adding this term to it and making that the value of theta dot. So I'm changing the variable. I don't have to keep track of all the individual ones, and that's really nice. This is not an algebraic equal sign. This is a make equal to sign. Now I need to update theta. Spell it right. Theta equals theta plus theta dot times dt. Now I need to update time. T plus dt. Okay. So if I do that, it's going to run and everything, but it's not going to change the display. I need to now move the ball, and I need to move the string. So I'm going to say ball.pos equals, it's the same thing it was before, right up here. I'm just going to copy that. But you notice that since theta changed, oh, I didn't copy the whole thing. Negative cosine theta, 0. But since theta changed, it's going to change. And let's just run this. Okay, I'm not going to update the string. I'm just going to run this. I didn't save it. Demo pendulum 1. Okay, run it. And you see, the string never moved, which looks kind of weird, but it looks like it's working very well, and it isn't working well. And it's in 3D. So I do need to move the string too. So let's go down here, and I don't need to change the position of the string, just the axis. So I can say string.axis equals ball.pos minus top.pos. Now I'm going to run it. And that's that. There's your nice visual of a mass swinging on a string. Okay, now there's another way to model this. I told you could model this with springs, and that's what we're going to do right now. Since we can't calculate that tension force, it's a force of constraint. One way to compensate that is to replace this string with a spring. Okay, so let's just go over to the paper over here real quick, and I'll explain how this will work. And then we'll do it. Okay, so I'm going to replace this with a string, this with the spring. So here's my new pendulum. Like that. So the nice thing about a spring is that I can indeed calculate the vector force due to a spring. So here's a spring of length L0, and now suppose I stretch it to some vector L. And this is the way they do it in matter interactions. My favorite textbook of all time. Check that one out. If you're not sure about it, let me know. I'll help you find it. And so now I can write the spring force depends on this amount of stretch, but I want the force as a vector value. So this is going to be Fs that way. So I can write this. Fs equals negative k times the stretch, which is going to be the magnitude of L, minus L0 times L hat. So here, if I have that vector L from the beginning to the end, I need that. I'll tell you why. I take the magnitude of that minus this unstretched length, and that gives me this positive value right here. So that's some positive stretch distance. K is the spring constant. It tells you how stiff the spring is. So this is a positive number. That's positive. L hat is a unit vector in the direction of L. So it has no magnet. It has a magnitude of 1. It doesn't change it. So I need the negative sign to say it's pulling back that way. So I need that because as this ball moves around, the direction of the force is going to change. But I can now say mg and Fs. So I have two forces on the mass, and I can use the momentum principle. So now I can say this. F net, which I can calculate, is the change in momentum with respect to time, where momentum is mass and velocity. Not mass. What am I doing? Mass, velocity. Okay. So now I can say, I can calculate that, right? F net is just going to be Fs vector plus mg vector. Yes, it's in the negative y direction, but we're still adding up the vectors. And that's going to be P2 minus P1 over delta t. So again, if I break this into small time steps, I can assume this is constant and use that to find my new momentum if I know my old momentum. So I'll say P2 equals P1 plus F net, which is that thing right there, delta t. And then once I know the new momentum, I can use that to update position. So I can say the velocity is P over m, and that's delta r over delta t. So I'm going to use r as a position of that. And it doesn't really matter where my my origin is. It doesn't matter. It matters about the change in this. So if I do this, I can say that's r2 minus r1 over delta t. So r2 equals r1 plus p2 over m delta t. And again, you see I'm using that trick. It's still a differential equation. I'm still solving a differential equation, but it just looks different, and it's a vector equation. And then I just keep repeating this over and over. So step one is to calculate the total force, use that to update the momentum, use that to update the position, repeat. Okay, so I had a string of length. I want to make it look great. Okay, so there's a trick. If I just do it right here, and I'll start it off like this, some angle theta, the same conditions before, it's not going to look great. Okay, so there's a trick. Here's the trick. If I start with the spring at the bottom, okay, and let's say I want this total length to be 1. I want it to be the pendulum like the other one. In that case, I can actually calculate. If I pick k, let's say k. I need mass. Let's say 0.05, 50 grams, and K of, let's just pick 100 newtons per meter. I'm just picking something. So the question is then, what would my unstretched length be, right? Because I have my spring. It has to be stretched if it's moving this way. It has to be stretched, okay? So I need some initial velocity, and that's actually a little bit of a trick. I didn't find that from the other one. Let's just pick a velocity down here. I could get a value. Let's say the magnitude of the velocity is 0.5 meters per second, and we can change that. If that's the velocity, I can actually calculate the unstretched length that would make this move in a circle. All right, so I really have some spring in here, L0. So this is nice because at that instant, I'm messing up my paper here. At that instant, I can say this. I have the gravitational force, mg. I have the spring force, fs. And then I know that the net force has to be up, right? Because it's moving in a circle. So in the y direction, I can say fs minus mg equals mv squared over r. Let's just call that r0 and r. I can use the l's though. Let's switch back to l. Over l. mv squared over L. That's L, right? And I want to, and L's 1 meter. I know my V, I know M, I know M, I know G, but I don't know the spring force I need, and I can use that to calculate my unstretched length. So this is just going to be Fs is mg plus mv squared over L, and that's going to be equal to the magnitude, that's going to be K times L minus L0. And just the magnitude, right? So I can use this to solve for L0. So I'm going to divide by K. So I get mg plus mv squared over L. All of that over K, the spring constant. And then I'm going to say L minus that. L0, L minus. Yeah. And that'll give me my unstretched length. And then when I put it in, it should move in a nice circle and won't move around too much. So I'm actually going to build this. I'm going to start with the same angle theta and show you that it doesn't work, and then change to this. No, I'm going to do it this way first and then go back the other way. Okay, so let's go back over to Python and make a new program. Okay, so let's save this one. Save it. Save. I think I saved it. And let's just copy it. Even though we need to change a bunch of stuff. Okay, the first thing I'm going to do is change this g to a vector. So it's going to be vector 0, negative 9.8. Oh, I got that. 0. Now the next thing I need is, I'll leave that theta there. I need the mass. Let's do it down here. So once I make my ball, I can say ball.m equals 0.05. ball dot P equals, I did say I was going to do it over here. So let's do theta is 0. Okay. So now it actually is right down, and I'll show you that in just a second. Let's just get rid of this whole thing. That's fine. Ball dot P equals ball dot M times vector. I said I want to move, I'm moving it to the negative x direction at 0.5 meters per second. So it's going to be negative 0.500. So that's my initial momentum. Now I need my K. K equals, I said 100. And then L0. L0. Now I'm just going to type in my equation. It's going to be L, which is 1, R, minus ball dot M times G, but I want the magnitude of G because I've now made G a vector. So it's going to be mag G plus ball dot M times V squared. Let's put this as like this. V0. V0 equals 0.5. I'll put that negative. It doesn't really it can go either way. Negative. So now I'm going to say ball dot M times V0 squared divided by the stretch length, which is R. And then all that is going to be divided by K. Let's just print L0. Just make. I'm feeling that it's not working. Okay, so the unstretched length that's pretty good. Okay, and it is. Wow. Okay, so now we can say t equals 0. We're going to make our loop while t is less than 3. Rate 100. The first thing I need to do is calculate the net force. I'll write it out. F net equals a ball dot M times G. That's my gravitational force. Now I need the spring force, which is going to be negative K times the magnitude of L minus L0. I didn't calculate L. Times L hat. So let's calculate L. L equals ball.pos minus top.pos. That's the vector from the top to the beginning. And it will change, right? Although we said we want it to be constant, it does technically change, and that's fine. It definitely changes direction. So that's the net force. Now I can use that to update the momentum. Ball.p equals ball.p plus F net times dt. Now I can update the position of the ball. Ball.pos equal, that's my R. That's R2. Ball.pos plus ball.p times dt divided by ball.m. I need to update the string, right? I don't want to make that mistake again. String.axis equals ball.pos minus top.pos. And update time. T equals t plus dt. I'm trying to think if I left something out. I don't know. Let's just run it. I didn't save it. Let's see. That's fine. It's saved as copy. I will give you the code to both of these in the link down below. Running it. I don't know. Oh. It did work. You can't even tell this is swinging, right? Let's increase that velocity to 0.8. I want it to be a little bit bigger. See? Looks the same, huh? It's pretty impressive. Okay, so let's say that, let's change it to theta equals 15 degrees, because I want to show you, or 20. So that's 0, it doesn't really matter. 20 times pi divided by 180. And then that's going to start over there. L0, let's say the unstretched length is 1. So I'm going to comment this out. L0 equals R. So, and so now what's going to happen is that it's going to start over here at some edge unstretched. And so when I let go, it's not gonna move just right. So everything else should be fine, I think. Let's run it and see. Yeah. See, you see how it's bouncing and everything because I didn't pre-stretch that spring. I mean, it's still pretty cool, but I didn't pre-stretch that spring. Okay, so let's go back to the way that we had it before with theta is 0. and then undo this because I want to show you one more thing. Let's make sure it's working. Let's increase the velocity even more to 1.8. Okay, so that's a pendulum, and it looks great, and we can compare it to the other one. Everything should be fine. This is a large angle mass. If you want to make a graph, you can make it. I'm not going to do that. You can make a graph and do this other stuff. I'm going to show you one more cool thing, and then I'm going to stop and let you go on with your day. And that is right over here. So this gives it initial velocity in the x direction. But what if it's also moving in the z direction? So let's give it a z velocity of v0 over 2. Does it matter? Oh, that does matter. Because now this is going to be v total. Let's be v total. It's going to be stretched. It's going to be moving faster. V total equals the square root of v0 squared plus v0 over 2. Actually, I should do this. Let's do this the smart way. Mag ball.p divided by ball.m. Right there, that's easier. So that gives me the total starting velocity. And so over here, instead of using just the velocity v0, I'm going to use v total. Right, so that will mean it'll be stretched even more because it's moving in 2 directions. Okay. Oh, that didn't work. Oh, I did the y direction. That's why. Dummy. v0 over 2. I was like, this is going to work. Like, what the heck's working? It's not working. Okay. Ball.p, it should be moving in 2 dimensions. Oh, you know what? It is. It just changed the initial launch angle. So I need to, let's do this. What I need to do is I'm going to stop. But what I need to do is I can print out the velocity at some final point right here and then give it an extra velocity. It won't be perfect, but I can get this to move in 2 dimensions. Trust me, it will work. Technically, this could work with a double pendulum, right? You can use the same idea of the springs with the double pendulum. And in worst case, you can always crank that spring constant up to some giant amount, and it should look a lot better. But I'm going to stop there. Those are the 2 ways I really want to focus on this visual aspect of creating the pendulum so that you could see how to make those visual things. Play with the code, look at my other video, and that's it. I'll talk to you guys later.